Good evening, everyone. Welcome to Minds 24 webinar series. We are actually very happy to see you all here. This is actually a webinar series that we have planned for discussing math in artificial intelligence and data science. So today, it is my great pleasure to welcome Professor Natarajan, professor in IST Trivandrum. Many of you might already know him because he is an pillar of excellence in the field of computational methods. And many of you know that he's a respected scholar from a prestigious Indian Institute of Technology, Madras. And his research areas include virtual element methods for nonlinear problems, stabilization of convection diffusion reaction equations, developing preconditioner for algebraic multigrid methods. With an impressive portfolio of publications and 15 years of teaching experience, Professor Natarajan has been a guiding force for many scholars, and his ability to convey complex topics with clarity and enthusiasm has always given him the acceptance among his community and students alike. So it is my pleasure to welcome Professor Natarajan to Minds 24. Today he will be talking to us on the topic vector calculus for machine learning. Welcome you, Professor. Greetings from IIT Kottayam. Over to you, sir.
Yeah. So am I audible? Yes, am I audible?
Yes, sir, you're audible.
Okay. Yeah.
Yes.
Okay, hello. So thanks Asha for such a generous introduction about me. Yeah, it's a good. Okay, fine. Okay, so I must. Okay. So today I will be discussing on I will give a title vector calculus and vector calculus for machine learning. How do you use it for machine learning? Okay. So let me share the screen. Is my screen the screen is visible? Are you able to see the screen?
Our screen is visible, but we are having an issue with
So now let us take the gradient of a vector valued functions. Now whatever we are seeing the function f, earlier it was a scalar. Now we are going to talk about the gradient which is of a vector valued. Okay. I'm going to talk about gradient which is a vector valued. Yeah. Okay. So here we try to define the function f. Since I mentioned it is a vector value, so it has to go from Rn. It takes n tuple and then it maps on to Rm. So that's why I call it as a vector value, where your m has to be greater than 1 and your n has to be greater than or equal to 1. Okay. Because m has to be simply greater than 1 because you need vector values. You need more than one output. Okay. The output should not be a single number. It has to be more than 1. So m greater than 1. And then of course it takes n variables. Okay. So this is how we try to define this function f. Okay. So this is the vector value functions. So this function, of course, your x is x1, x2 is an n tuple, xn, which is a transpose, because usually it's a column vector. So whenever we write it as a row, we try to make it as a transpose. This belongs to Rn. Now how do we discuss our f of x? Our f of x can be discussed as a vector, column vector, which is nothing but f1 of x, f2 of x, etc. There are m components of the function fm of x. So this belongs to Rm now. So your output is a vector value of m components. So when we write this way, it's much more easier for us to see this function as a vector valued. That is, we can simply denote it as f1, f2, etc. fm. We can denote this vector f. Simply f can be written as this vector of functions, and each function fi takes values from Rn to R. Okay. Each fi can take values from Rn to R. Now, when we talk about the differentiation, how do we differentiate these variables? When we talk about the partial derivative of these variables, when we talk about the partial derivatives of these variables, how do we define the partial derivative? So we say about dou f by dou xi, the partial derivative. And you remember your f is a vector valued, it's a vector m components, vector which has m components. So when we try to differentiate it, dou f upon dou xi, of course your xi is an n-tuple. So whenever we try to differentiate this, dou f by dou xi, so I can write this as dou f by, so this is basically dou f1 by dou xi, dou f2 by dou xi, etc. dou fm by dou xi. Okay, and then you know, of course, this belongs to Rm. This belongs to Rm, and this derivative, each derivative, you know, how do we compute these derivatives? From the first principles, you take f, f1, x1, x2, etc. I'm differentiating this to I, so this will be xi plus h, comma xi plus 1, etc. xn minus f1 of x divided by h. So like this, you are going to put all the components. Similarly, f2 is going to be f2 of x1, x2, etc. Again, xi plus I plus h, xn minus f2 of x upon h. Okay. Similarly, you are going to do it for m also. Okay, that's fine. Basic first principle. Okay. So this is how we are trying to define the partial derivative. Okay. So the gradient of f with respect to a vector is a row vector of partial derivatives. Okay. So we obtain the gradient with respect to x by, so what we do is we try to collect the partial derivatives. So as I mentioned, whenever I talk about dou f by dou df by dx, that's a gradient. And I mentioned this as a row vector. We are not going to place this as a column vector, it's a row vector. So it is dou f by dou x1, etc. dou f by dou xn. And remember now, our case, your f is going to be a vector valued, so your f has m components. So upon substituting this again, so this gives rise to a matrix. So we are going to get now a matrix dou f by dou x1. So replace each one by, so dou f1 by dou x1, that gives you a column, dou f2 by dou x1, etc. dou fm by, and here again dou f1 by dou x2, dou f2 by dou x2, etc. dou fm by dou x2, and here etc. Here is going to be dou f1 by dou xm, dou f2 by dou xm, etc. dou fm by dou xm. Okay. I think we need to use n here. Sorry, it's not m. Only f has m components. Your x is going to have n components. So this is going to be replaced as n. Okay. Okay. So only f1, f2 you are varying, and it is partially differentiated with respect to xn. So in the vector valued case, we see that the gradient is going to become a matrix. The gradient has changed into a matrix. So we get into a matrix here which is m by n, matrix of size m by n. So this is what now we try to give this. This is what we call as the Jacobian. Okay. So the Jacobian matrix. So we call this as J. So this is equals to grade xf. When f is a vector valued function, we are going to get into the Jacobian, or in a matrix notation we can also write it as capital J I J is dou fi by dou in the index notation, matrix index notation. We can also write it like this. Okay. Now, suppose we need to find the gradient. Suppose I have for an example, suppose I have something like this. Suppose we are given, for example, let us take an example. Suppose consider f of x is a linear model. Okay, for a linear model, f of x is ax, where your f of x is Rm as usual, and your A is a m by n matrix, and your x is an n tuple. Okay. In order to compute the gradient df by dx, okay. So what do we do? So df by dx. So we can represent our, first of all, we try to represent our f in I index notation. So when you represent your f in the index notation, it's going to be f I of x is going to be summation aij xj. J varies from 1 to n, which improves. So that is basically, so your dou fi by dou xj is going to be simply aij. This is going to be simply aij. Now if we try to collect the partial derivatives, so basically if we write this as df by dx will be equal to, basically, so it's going to be dou f by dou f1 by dou x1, as we wrote earlier, dou fm by dou x1, etc. Dou fm by dou xn, dou fm by dou f1 by dou xn, dou fm by dou xn. This is the matrix. So this is going to be basically nothing but your A matrix. You are going to get the A matrix, A11, etc., A1n, AM1, etc., AMN. So that gives you A, which is your m by n matrix. Just in the case of linear model, and the model is linear, f of x is ax, then we see that the gradient of x, which is a Jacobian matrix, is going to be like this. This is just to give a typical example of what we are doing. Okay. Now, when we talk about the the real practical problem, okay. So linear, as I mentioned, this is where the linear regression. In the context of linear regression, we need, so what we do, we need in the context of linear regression, we need the derivatives of the least squares, derivatives of the least squares loss, least squares loss L with respect to parameters theta. With respect to parameter theta. So how can we talk about this? That is basically we are trying to talk about least squares loss. Okay. Now how do we model this? Okay. Suppose again, if I look into, so basically we are trying to talk about now the gradient of a least squares loss in a linear model. Okay, if you have a linear model, and then when you talk about the gradient of the least square loss, okay, so how do we go about it? Okay, so if you model this as since I mentioned linear model, so let me write it as y equals to phi theta. Let me write it as y equals to phi theta. Okay, so theta is nothing but is a parameter vector. Theta belongs to Rd. This is a parameter vector. And phi belongs to so Rn by d. It's going to be a matrix. These are nothing but input features. And our y is going to be nothing but y is from Rn. These are nothing but these are observations. Okay, they are the observations. This is with respect to the linear regression. Okay. Okay. Now, since we wanted to do an optimization kind of thing here, so what we want to do is, so what we do, so we go for, we define some set of functions. Okay. Let us define set of functions. First, let me talk about L of E. That is the loss. Okay. Let me define the loss as L of E with norm of E square. Okay. Okay, and then what is your E? So E of theta, I'm going to define E of theta as y minus phi theta. Okay, that is the loss. Okay, so we are essentially going to talk about the least square loss. So that is why y minus phi theta least square. I'm making the square. That's your L. L of E is the objective function, which is making the least square, and your E of theta is the model thing. That's the loss y minus phi theta. Okay. Now what we want here? So what we want is from the gradient, again from the gradient idea, we are seeking. So we want to look for dou L by dou theta. Okay. Of course, we need to use a chain rule. Okay. So this L, we try to call this L as the least squares loss function. Okay. L is nothing but the least squares loss function. Okay, so obviously, so whenever I wanted to compute this dou L by dou theta, the basic idea is to use the chain rule. Okay, so dou L by dou theta is going to be nothing but dou L by, so this is where you have dou L, so this is going to be dou L by dou E into dou E by dou theta, dou E by dou theta. Okay. So whenever, so for the corresponding element, this can also be written as dou L by dou theta of 1 comma d. I can write it as summation dou L by dou E of n, dou E by dou theta with respect to n and d. Okay, with respect to n comma d. So this is basically the dth element. I am trying to talk about the dth element. Dth element of dou L by dou theta, we can get like this. Okay, we know that our norm E square is basically, it is written as like this. So we can determine, using this we can determine dou L by dou E. So what will happen to our dou L by dou E? Dou L by dou E is going to be, so dou L by dou E we can write it as 2 times, this is E transpose E. That's going to be 2 times E transpose. Okay, you can we can write E also. Of course, basically it is a x1 square plus x2. Similarly, it's going to be E1 square plus E2 square, etc. like that. So once you do that, you're getting 2 times E1. So basically, it is 2 times the E transpose. That's what you will get. So you make it, write it E or E transpose. We write it E transpose because of the dimensionality. You want to stick to dimensionality. So I want to make it as a row vector. That's why we use E transpose. 2 times E transpose. Okay. Now again, so then what about dou E by, so we need a dou L by dou E, and then we need dou E by dou theta. So you know what is your dou E by dou theta? Dou E by dou theta is going to be minus phi. Dou E by dou theta is going to be minus phi. Okay. So this my phi, you know, it belongs to Rn by d. Now we need to club it to get our dou L by dou theta. So how do we talk about dou L by dou theta? So dou L by dou theta is going to be the product is a product of dou L by dou E into dou E by dou theta. So that is 2E transpose into phi minus 2E transpose into phi. Okay. Again, that can be simplified minus 2. So we can expand it y transpose minus theta transpose phi transpose into phi. Of course, this is R1 by D. So these components are going to give you 1 by n, and your phi is going to be n by d. So that finally gives you 1 by d. Of course, you could have tried this without using the chain rule also. Okay, you could have looked at the directly. You could have looked at the function like this. Directly, I could have wrote this as some L2 of theta equal to norm of y minus phi theta. That is your e norm of e square. That is, you can expand it as phi theta into y minus phi theta. Because here the transpose into this. Now this approach would also we could have tried. Instead of this approach, we could have tried this approach also. But here the practical problem is for deep functions, when you have in deep learning, you have for deep functions compositions, when you have compositions of deep functions. Okay. In the case of deep function compositions, okay, this becomes impractical. This kind of things becomes, because you have several compositions, this will become impractical. So that's why we need to resort to only to the first approach what we have done here, this approach. Okay. Now, how do we talk about the gradient of matrices? Can we look into the gradient of matrices? Can we look into the gradient of matrices? Okay, we have seen the gradient of a scalar valued. Then we talk about a gradient of a vector valued. Okay. Now can we talk about the gradient of a matrix? Okay. How do we discuss the gradient of the matrices? Okay. Or we will try to gradient of vectors, or I try to write it as gradient of vectors with respect to matrices. Gradient of vectors with respect to matrices. Okay. Gradient of vectors with respect to matrices. Okay. So how do we do that? Again, suppose I consider the linear model f equals to ax. Okay. With the standard error f is in Rm. A is Rm by n, and your x is in Rm. Okay. Again, now we are trying to talk about the gradient with respect to matrix. So that means basically we are trying to talk about df by dA, df by dA, the gradient with respect to a matrix, okay, not with respect to x. Okay. Now again, this gradient of dou f by dou A means it's basically nothing but the collection of all partial derivatives. So now the partial derivative is going to be with respect to the matrix, dou f1 by dou A, etc. Dou f m by dou A. Okay. So each dou fi by dou A is going to be a from R1 1 by m by n. So this is fi, each fi with respect to A, if you are going to differentiate, that's going to give you m by n. That is means a row of m by n, one value of m by n. Okay, that's what you are going to get for each times. Okay. So essentially, the full collection, we cannot make the full collection here. It may be like a tensor, sort of a tensor kind of thing. Okay. Now, if you write explicitly, if you write this in your usual notation, f equals to ax, if you write it as fi is nothing but summation aij xj, j varies from 1 to n, where your I varies from 1 to etc. m components of f. Okay. Then what happens to its partial derivatives? The partial derivatives are going to be dou fi by dou capital A. I make it as iq. The second index I make it as q. So if you do this, we are going to get something like xq. Okay. Which you can see. Suppose you have a11, a12. In general, for two, just 2 by 2 matrix case, you can see this. So this is a11 x1, a12 x2, etc. So once we differentiate this, so this will be f1 and f2, just for two case, okay, two value case, okay. And then this basically when you differentiate dou f1 by dou aiq. Suppose it is I means I talks about the row, okay. So if if this I is the row and you are varying the column, q varies the column, so can be I1, I2, etc. Accordingly, we are going to get x1 or x2. That's why you are going to get here xq when you differentiate dou f by dou aiq. So you can treat I as a row, and then q varies. In this case, 1 and 2 I mentioned. In general, it can be we have I varies from 1 to m, and then the other one will vary from 1 to n. Okay. So yeah, so this is the derivative which you are trying to talk about. So this we can write this as, in fact, we can write this one as dou fi by dou e. As I mentioned, it is a ith row. I can write it as I comma colon. Simply I can place it as I comma colon. Dou fi by dou e I comma colon. That is going to be simply nothing but, so if you choose ith row, it's going to give you simply x1, x2, xn. Okay, so that's basically nothing but the row vector. That's the x1. That is basically nothing but your. So this should give you precisely x1, x2, etc., xn, and this is precisely nothing but x transpose, because this is a column vector. So this is basically, we can denote this as 1 by n. Okay. And similarly, if we talk about suppose dou f by dou ai comma colon, that's ith row with respect to the differentiating with respect to the ith row of the matrix A. Similarly, if we can talk about the index are varying, suppose dou fi by dou ak, where this k is not equal to I, comma, and then I talk about colon for all columns. You talk about a kth row, that kth row is not your I. When you differentiate dou fi by dou ak, which is not your ith row, and for all its column, so that's going to be basically 0. All the entries are going to be 0. So basically it is 0 transpose. Okay. That means there is 0 entries, all the entries are 0. That's what you need to understand. Okay. If you want to precise, just make this as 0 entry. Simply we are going to get 0 entries. 0 comma 0 comma etc. 0, and that is 0 transpose. Again, that is going to be r1 by 1 by n. Okay. So now we can club all these things and put our we can make our gradient dou fi by dou e. We can make the gradient as, so remember, only dou fi by dou ak, only when k equals to I, you are going to get this x vector. Otherwise, it's going to be 0. So simply it's going to be nothing but 0 transpose, etc. 0 transpose, then x transpose. That's for the ith ai, for the dou fi by dou ai component, and then remaining components are 0. Okay. So this is going to belong to R of 1 by. Now you have this m component, so it should be m by n. Okay. So R1 by 1 by n, etc. Now it will be going to be m components. So you are going to get R1 by m by n. Okay. Similarly, we can also talk about we can also talk about gradient of matrices with respect to matrices. Okay. And then I will go to application. I will do one more and then we'll move on to an application. I will highlight that application. Okay. So one more I will try to say that is nothing but gradient of matrices with respect to matrices. Okay. So suppose I consider a matrix R from your m by n matrix and the function f from m by n to n by n. You can write the objective function in terms of this matrix R, f of R, because it depends on the matrix. Okay. R transpose R. It's not simply vector valued, and then this is, if I can consider some k, which is again R n by n. So it takes a matrix as an input, and again your output is also a matrix. Okay. Here we are going to look in for the gradient of f. So that is basically we are going to talk about the gradient, which is nothing but dou k upon actually is d. We are talking about the gradient. So the gradient is going to be dk by dr. Okay. Remember the R is a matrix now. Okay. So the output is also a matrix, and your input is also a matrix. Okay. Dou k by dou r. Of course, this is a hard problem. Okay. Now we will write the gradient. Okay. So this is a tensor. Now what we are going to have is a tensor. So we know that we can say this dou kpq by dou r. Okay. This is going to be of the dimension 1 by m by n. That means a matrix. This itself gives you a matrix. That is 1 by m by n. So one matrix it gives us an output. And then if we collect it all, we need to get something like, okay. So this is true for p comma q is 1, 2, etc. n. Both p and q are varying. Okay. That's why you are getting it as a matrix. Okay. Where this we call kpq is nothing but it is the pqth entry of k, that is your f of r, because k is a matrix. Okay. Now let us denote the ith column. So the ith column of r by ri, small ri. So what we can write? So we can write kpq as rp transpose rq. That is the dot product. Basically, we are trying to use the dot product, and then dot product of two columns of R. Okay, that is every entry. So what does this mean? That is every entry of K is given by is nothing but the dot product of two columns. Dot product of two columns of R. Each entry of K is obtained by the dot product of two columns of R. Simple, two columns of the matrix R. Okay. Two column of the matrix R. Every entry of the K, that is KPQ, is nothing but the dot product of two columns of the R matrix. So that if you want to write this, we can write in terms of the matrix notation. Okay. So because we are denoting RP means it is nothing but the pth column of capital R. That's the notation meaning. Okay. Okay. So okay, R by Ri means so it is the ith column of R by Ri we are denoting. So RP means it is the pth column of capital R. This can be written as RMP into RMQ. M varies from 1 to M. Okay. Now we can talk about the partial derivative. So dou KPQ by dou Rij. This is going to be summation dou by dou Rij of Rmp Rmq. Okay, m varies from 1 to m. This is, we are trying to compute the partial derivative. We are using this relation, and then we wanted the partial derivative. This is dou by dou Ri j of this component, this summation component. Okay, varying over m. So this is going to give you something like dou p q I j. We are denoting by this notation. What is this dou p I? Dou p q I j. So dou p q I j is going to be, we can define it as Riq, if j equals to p and p not equal to q, or Ip, j equals to q and p not equal to q, and then it is 2 Riq. Of course, if you do this with the summation, you will get this 0 otherwise. J equal to p equal to q. Okay, 0 otherwise. So this is the gradient which we try to get when we have a gradient. The input is also a matrix and the output is also a matrix. Gradient of matrices with respect to matrices. Okay, and then of course with useful some computing gradients. Okay, so the gradients frequently used in machine learning. There are some kind of gradient which are frequently used in machine learning. Okay, I will just put the reference here. You can go and look into the reference. This reference. Yeah, you can look into this reference. There are several gradients which are useful in machine learning. These are provided in this book by Peterson and Pedersen, 2012. Okay. Okay. And then you have, for example, I just give you some example. You can look into all sorts of this identities. These are basically identities. Some of the identities are dou x by dou capital X of f of x transpose will be going to be dou e of x by dou x transpose. Okay, and suppose dou by dou x of just one or two identities I am listing. For a full detail, you can refer this particular reference. It's going to be trace of dou f of x by dou x. Okay. Okay. So there are several such identities are there. Okay. So you see, basically the derivatives are not simply matrices. Sometimes they are tensors. They are turns out to be tensors, higher dimensional tensors. Now let us come to again machine learning application. Let us again talk about some machine learning application here. Okay. So okay. So whenever we find some good model parameters, so in order to find some good model parameters, we perform the gradient descent. Okay. Traditionally in machine learning, okay, to obtain or to find good model parameters, what we do basically is we use what is called as the gradient descent. We perform the gradient descent, which you are familiar. This is a very famous algorithm, the gradient descent. Okay. Okay. So basically, what we do gradient descent means we are trying to obtain the gradient of a objective with respect to the parameters of the model. So you so what you do, you try to compute the gradient of the objective function, the gradient of, we call it as a learning objective. Okay, gradient of a learning objective with respect to model parameters. Okay, with respect to parameters of the model. For example, suppose let us consider the example here. Okay, suppose consider f of x is equal to square root of x square plus e to the power x square plus x square again e to cosine of this. Okay. Now, of course, now we can apply the chain rule here, and the differentiation is linear. So if we talk about here the gradient df by dx, okay, this is nothing but first case 2x plus 2x e to the power x square by 2 times square root of x square plus e to the power x square minus sinusoidal of x square plus e to the power x square 2x plus 2x times e to the power x. Simply we are using the chain rule. Okay. And then we can rewrite it this as, I can pull 2x common, of course. So 1 plus e to the power x square will be there. So I can write 1 by 2 times of square root of x square plus e to the power x square minus sine of x square plus e to the power x square into 1 plus e to the power x square. Okay. Now, writing the gradient, this is also we have wrote. So, writing this gradient is, it involves a lengthy expression. Okay, you see there is a lengthy expression. So, writing the gradient in this way gives you a lengthy expression. Gives a lengthy expression for the derivative. Okay, gives lengthy expression for the derivative. Okay. So that means in practice, when you calculate, if you are not careful, the implementation of the gradient will be significantly expensive. So computationally, you see that this computation, maybe if you are not careful, computationally this evaluation, gradient computations, will be computationally expensive. It can become computationally expensive. Okay. Than computing the function. Okay, more than the function, this becomes more complicated to do this compute. Okay, so this poses an extra computational overhead. Okay, it gives an extra computational overhead. So what people do is there is a specific. I'm not going to do that, but I just mentioned in order to overcome this, basically in the deep neural network. Okay, in deep neural network model. Okay, to overcome. So to overcome this, what people do is, in order to overcome this, they use a specific algorithm which is called as back propagation algorithm. Okay. This is called as a back propagation algorithm. Okay. Of course, you can refer to some of the works by Kelly 1960 and Bryson 1961. Okay. These algorithms are so this provides an efficient way to compute the gradient of the error function. So this backpropagation algorithm provides you, what does it do? It gives you an efficient way of computing the gradient. Efficient way of computing. Remember, we are talking about from the computational point of view. Efficient way of computing the gradient. Efficient way of computing the gradient with respect to the model parameter. Okay. Okay, now finally I will try to move on to a simple case. One simple case, suppose, okay, in a deep learning, if you see in the extreme deep learning case, usually it involves many level function composition. Suppose you try to compute y, it involves many compositions, composing, evaluating several composition of functions. Okay. It involves several composition of functions evaluated at x. Okay. Of course, x is your inputs. X are your inputs. Okay. Then y are the observations. Observations. Input means these inputs can be images. For example, observation. Observation can be class labels. Okay. Observation can be class labels. Okay. Okay, so if once you have this kind of compositions, okay, so this is in neural network. What we do in neural network, if you have multiple layers, okay, if you have a neural network with multiple layers, okay. Suppose I you have a function something like this, fi at xi minus 1 can be written as sigma of ai minus 1. Um, Asha, hello, Madam Asha is there?
Yes, sir.
So when should I close?
I think, sir, by 7.
Okay, couple of minutes more.
Yes.
Okay, fine. Yeah. So suppose consider the function is of this form. Suppose, for example, the function is given like this. Okay. This is in the ith layer. Suppose the ith layer, you have several layers. Okay. Now suppose in the ith layer you have the function like this. Okay. So xi minus 1 is basically the output at the layer I minus 1. This is nothing but the output at the layer I minus 1. Okay. And sigma is some activation function. Okay. It can be any activation function. So when we talk about the gradient of a loss function L, whatever we earlier we tried to do, okay. So the gradient of the so we need to compute the gradient of this L. So you first define the gradient of a loss function, which we defined earlier, L of that E, and then we try to define the gradient. We try to find the gradient of the loss function. So we are interested here first to define. You need to define the loss function, and then we need to talk about the gradient of the loss function. Gradient of the loss function. We talk about the gradient of the loss function. Okay. Yeah. So suppose the neural network. So suppose we provide a structure something like this. Initially, f naught is x, and then each fi is recursively defined as sigma I ai minus 1, fi minus 1 plus bi minus 1. I varies from 1 to k. Typical network this is an example of a network model. Okay. And then we define the last function. The last function L of theta is norm of y minus fk of theta x norm square. So of course, now we need to talk about the gradient of this L. That is what we are interested in. And then suppose I try to talk about the parameters. Theta j is nothing but aj comma bj. Okay. Okay. For each layer you have 0, 1, 2, etc. k minus 1. Okay. So now using the chain rules, we can see that we can evaluate this as dou L by dou theta k minus 1. So you see here, when we differentiate this dou L with respect to theta k minus 1, the function fi depends on this ai minus 1, fi minus 1. So here there is no problem. Simply we can get it as this is, so your L is nothing but depends on fk, and your fk is going to be depending on these parameters recursively. So directly we can do it as dou L by dou fk first, and then simply you can say dou fk can be differentiated with respect to theta k minus 1. Okay. When we do with the lower order theta k minus 2, of course we cannot do dou L by dou f by dou theta k minus 1 is not possible. This is not possible. Whenever you do theta k minus 1, you cannot do simply dou fk by dou theta k minus 2, because only your fk minus 1 involves theta k minus 2. So we need to differentiate with respect to k minus 1. Then only k minus 1 can be differentiated with respect to theta k minus 2. Because only k minus 1 will get this parameter of theta k minus 2. So likewise, if you keep on do this like this, dou L by dou theta I in general can be dou L by dou fk, dou fk by dou fk minus 1, etc. Dou f I plus 2 by dou f I plus 1, and then dou f I plus 1 by dou theta I. That is the fi which will contain theta I. Understand? So that is how you see always dou f k minus 1 contains only that you can differentiate with respect to k minus 2. So I plus 1, then only you can differentiate with respect to theta I. Okay. Okay, fine. So, yeah, so okay. So this is how we try to do the gradients. Okay. And then as I mentioned, we need to use certain algorithms. In the initial case I mentioned, try to look into this back propagation algorithm. Okay. And there are some other concepts which are, due to lack of time, I just mentioned that there are some more topics are there, something as automatic differentiation. This is one more topic which involves vector calculus idea, the gradient, whatever we used. Okay, automatic differentiation. Okay, so so this is actually more generalization. This is a more general compared to back propagation. Okay, so back propagation is a particular case of this automatic differentiation. Okay, back propagation algorithm. Okay, this is more general. The automatic differentiation becomes more general. Okay, so how do we compute this iteratively? Okay, okay, fine. I could not tell more about that part. Okay, okay, yeah, okay, Madam Asha. Okay, I would like to stop. Yeah, thank you.
Okay, sir. Okay, thank you.
Any
Uh,
questions?
yes, sir. If participants have any questions, please unmute yourself and ask, or else you can post it in the chat box also. Sir, actually, one participant has requested if you can provide the PDF of this, it would be good.
Yes, yes, yes. Since I have wrote this as a material, I can send the PDF to you. Yeah, yeah. No
Okay,
problem.
sir. Okay, thank you. Thank you. Thank you so much. Okay, sir. If there are no questions, I would like to invite Dr. Murugan for vote of thanks. Over to you, Dr. Murugan.
Yeah, good evening, everyone. First of all, my greetings to all our participants, Mind 24 webinar series. First and foremost, I would like to extend my thanks to our director, Professor Raju Daraskar, and our Honorable Registrar Sir M. Dr. Radhakrishnan, and our Professor in charge, Mohanan, and our head of the department, Dr. Danya Ma'am. They are given a constant support and behind all our success. Thank you, ma'am. Thank you, sir. And I extend my thanks to my coordinator, Dr. Asha also. Then especially special thanks to Natarajan sir. First of all, accept our invitation and wonderful this session. I remember in my mind, sir, I'll continuously attend your sixth lecture. So I feel every time you are given a different kind of feast. Today also one. My mind is correct. First of all, I attend in NITC, NIT, finite difference, and the second one more lecture is a finite element, and Karakkudi University also linear algebra. Then our institute also system of equation. Then now that machine learning area. Every time you are talking is inspire me, sir. A very new computation ideas are we learn. Special thanks for your reference book. Thank you, sir. And because of IEEE equal time, I would like to once again thank you, sir. Now next I extend my thanks to our technical support team, Siju sir and his teammates. Special thanks to our all participants. You are eagerly joined with us. I assure you that you will get back everything soon. In this time, I just remember my professor's statement. Uh, Need not do many things in a day. At least you have to learn one thing per day. It is enough for you. So I hope that many are gets at least one point of view, new knowledge in that session. So once again, I thank you all. Thank you.
Thank you, Murugan sir. So today's session we are winding up. Thank you, participants, for joining us. On next Wednesday, we will have Dr. Divya Sindhu Lega from IIIT. She'll be sharing on graph theory-based data analysis. So thank you. Thank you once again for joining. You may leave. So with this, we are concluding the session. Thank you. Karan, you can just end the session. Thank you.